All right, so we're going to talk about atoms today. A little bit about atoms, a little bit about matter, a little bit of how that relates to physical therapy. So we're going to start with the absolute most basic stuff. We're going to talk about atoms, molecules, some common atomic matter and PT. And then we'll talk about the properties of matter, solids, liquids, gases, plasmas, and kind of how they relate to us. Yes, I am recording. I am screen sharing. Okay, good. So first of all, we talk about this is that glorious periodic table. So the good news to let you guys know, for your final in physics, you only have to memorize up to the first 90 parts of the periodic table. We're going to rule out 90 to 115 because of the unstable elements. I'm just joking. You don't have to memorize any of them. Diana's like, please say you're joking. Please say you're joking.
Wow.
I didn't believe that one.
You had me there.
I had you a little bit, right? But what we will talk about, there's a chart coming up that has specific charges of ions. Those you will have to not only know for this class, but we're also going to know it for modalities coming up next semester. So that's why we're going to talk about this. So when we talk about the periodic table, right, the number above the element in the periodic table is the atomic mass. What's making up the nucleus of the atom, right? So when a substance is made up only of one type of atom, we call that substance an element, right? Oxygen, hydrogen, helium. The elements are arranged for our knowledge in what's known as periodic table of elements, right? The word atom and element can be used interchangeably because we're only talking about one item on the periodic table. There are 115 that we know, 90 occur in nature, and then the remaining 25 obviously are very unstable and just kind of break down rapidly. A lot of them are human created. We're always trying to create new atoms, which I'm not so sure is always the best idea, right? You know, the CERN collider and everything like that, where we're banging atoms against each other just to see what happens. One of these times something's going to happen bad there, I'm pretty sure, and we're going to end up with, you know, which one? That was Angels and Demons, wasn't it? The one book with, or the one movie in the book with Tom Hanks where they're talking about the CERN collider and all that problems happening. I think it was. It's been a while since I watched that and read that too. But associative knowledge, so you don't have to know all of the elements, thankfully. We're not going to encounter all of them in physical therapy, right? But we do kind of have a key list that we will deal with. And so these are the kind of ones you will deal with on a fairly regular basis, not only in physical therapy, but also through your studies in physical therapy, right? So sodium, potassium are important, right? Sodium, potassium, and calcium are all important in what? Does anyone know what those are really important in? Nerve conduction, right? The conduction of signals down your nerves to allow your muscles to contract. Sodium and potassium, especially with the sodium potassium pumps, right? Chlorine, carbon, we're going to talk about that a bit. Nitrogen, titanium is used heavily in physical therapy, actually post-surgical physical therapy, because titanium is what a lot of the joint components are made of when people have joint replacements. Iron, as we call it back in Pennsylvania, right? What do you call, so if you take iron and you arrange it in a circle, what do you call that? Does anyone know?
Stonehenge.
It's a Ferris wheel. It's starting to sink in. Seeing the faces. Iron's, you know, Latin term is Ferris, right? So Ferris wheel, Stonehenge. I like that too. Silver. Does anyone know what we use silver for in physical therapy? Other than to repel werewolves? Doesn't work. I've tried with some of my patients. Doesn't repel them. We use silver in wound care because silver has heavy antimicrobial properties that it's really good at kind of drawing out bacteria. For some reason, bacteria is kind of attracted to silver. So we can impregnate dressings with a silver solution, and that kind of helps keep those from getting infected or help heal them when they are infected. You got magnesium, barium. I barely knew him, but I did barium. Cobalt, zinc, oxygen, and hydrogen obviously are pretty big as well for water and breathing. So these are the most common compounds you're going to encounter when we're dealing with iontophoresis, which we'll talk about next semester, right? But iontophoresis, right? Whenever you see a phoresis, we're delivering medication, right? Because we have phonophoresis and iontophoresis. Phonophoresis is the delivery of medication via sound, via using ultrasound. Ionto meaning ions, so we're delivering it via electricity. This is pretty much all of what you're going to encounter in iontophoresis. Even phonophoresis, we use a lot of these. But the reason you need to know these is if you are doing iontophoresis with a patient, you have to know their charge, because when you get the little iontophoresis kit, right, there's going to be a red pad and there's going to be a black pad. What do you think those are to indicate?
Positive and negative.
Positive and negative. Which color is positive?
I think red.
Good, right? Positive, negative. Well, we're going to talk about some properties of atoms in a little bit, but the reason you have to know this is if you are using a negative medication, you need to put that on the negative pad. Why do you think that would be? Anyone have any ideas? What happens when you have charges that are alike? So if you take two negative poles of a magnet and try to put it together, what happens?
They repel.
They repel, right? So if we put the negative medication on a negative pad, when you turn that pad on, it's going to push the medication into the skin because it's going to try to repel it, right? So if I'm doing iontophoresis maybe on, I've got tennis elbow, and I put the pad right there for it, I put the negative pad there if I'm using negative medication, and I can put the positive pad down here. And what's that positive pad going to help do? If the negative's repelling, the positive's going to attract it. Yeah. So it's going to help. This is going to push the medication in. This is going to help pull the medication in. That means the medication itself will go a little bit deeper. Therefore, a better chance at actually treating it, right? So we have some common medications here, right? Usually we're talking about acids and bases, which is the easiest way to look at it, right? Acetic acid, I've talked briefly about. We usually for calcifications and myositis ossificans, which is calcification of a muscle. I just put this up, so yes, it should be updated shortly. John, I just edited the PowerPoint about 5 minutes ago, so it should update in the next 10 minutes. So I just forgot to add this slide, so I just added it. And I also put up, there is an Excel sheet with it up there as well for you if you just wanted to print this slide. So acetic acid, obviously when you see acid type stuff, it's usually to break down. So calcifications, calcifications of tendons. In myositis ossification, that's where the muscles are getting inflamed and they start kind of turning to bone. Calcium chloride used in scar tissue. We use it to kind of break down really hot, heavy keloid scarring, right? And it can even be used in muscle spasms for people that have really, really heavy spastic muscles. Copper sulfate we use for fungal infections, again, in wound care. And if you notice, there's not a lot of positive stuff here. It's mostly all negative. That's a pretty good guess. If you get a question on your boards where your boards are asking you, is this medication a positive or negative medication? Usually a safe bet to go probably negative. There's not too much that's a positive medication. Unless we're dealing with something like that copper sulfate, lidocaine, and magnesium sulfate, right? Iodine, where do we take iodine in every day? Where do we take iodine in every day? What's got iodine in it?
Salt.
Salt. Yeah. Why did we add iodine to salt? Does anyone know? It really doesn't occur in food too regularly, right? So the easy way to add it is via salt, because pretty much everyone adds salt to their food, right? So you add that to salt and it allows us to get it. Iodine is really useful in preventing, nuclear, because especially like if you're exposed to nuclear waste, they're going to give you high doses of iodine to kind of help treat that. Again, it's really useful, especially in wound care. We use iodine. Lidocaine. Lidocaine is used for pain relief, right? You often hear about something like Salonpas' lidocaine patch. Lidocaine is a lesser version of Novocaine, right? What do you use Novocaine for? Where do you hear that often used?
Dentist.
Dentist, yeah, right? They inject it into your mouth, and that's when you get the drooling effect from your mouth, right? Because the whole area just goes, right? Where you have a stroke, one of the two. But looking at that, and you look at if you actually look at the chemical structure of lidocaine, and you look at the chemical structure of novocaine, it's actually not that far away from, guess what? Cocaine. The actual chemical structures are not that different. And it's kind of funny because for people that actually snort cocaine, or so I hear, their nostrils go numb. Well, it's because it has similar properties to what everything else has here. MgSO4 magnesium sulfate's really used. The main thing we use it for is muscle spasms, especially patients that might be a spinal cord injury or a stroke. Again, you don't have to know the specific diagnoses yet. Salicylic acid, I guarantee probably somebody in this class used salicylic acid this morning. Does anyone know what salicylic acid comes in quite frequently? Face wash. Yep. Right. It's used to treat acne. But it's really common, again, to use for plantar warts is the main thing. We'll say for occasionally for muscle and joint pain. I haven't seen that as frequently, but plantar warts definitely, because we will treat those occasionally. And then zinc oxide we'll use in conjunction a lot of times with iodine for tissue healing, especially in dermal ulcers is the old term. I should really change this slide a little bit. Does anyone know what the new term for dermal ulcers are? We stopped using dermal ulcers and we now call them pressure injuries. And the reason we changed, ulceration occurs naturally. Right now, that was a really good S. Right now, I have an ulceration in the back of my mouth because I had a bunch of warheads. I was sitting here earlier and I was munching on warheads. And now I've got you know how you get that nice sore spot from eating a bunch of sour candy? I got one of those in the back of my mouth. That's an ulceration. That happens naturally. When we talk about dermal ulcers or pressure ulcers, those aren't a natural occurring affair, right? Those are caused because we don't take care of the patient. So literally what we are doing is providing the patient with an injury. So we've changed the term from pressure ulcers or dermal ulcers to pressure injuries, indicating that they should be preventable, and we typically don't. And that's how patients have real bad problems with it, right? So composition of all living things. Pretty much everything that lives has oxygen, carbon, hydrogen, nitrogen, and calcium. And it's really interesting that if you look at organic by chemistry or biological sense, an organic object must contain carbon chains, right? That means all food that you eat theoretically is organic, right? Do you ever question that when you go to someplace and it lists something as organic? You're like, is this really organic food, or is this are they just saying it's organic? Well, theoretically, by the definition of organic, they can classify you could classify ramen as organic ramen if you really wanted to, because it's made up of carbon chains. Hopefully people that are doing organic foods aren't classifying that as that, but you could. So when we look at the structure, right, we talk about the nucleus and we'll talk about the electrons as well. The atomic nucleus is most of the mass of an atom, right, or an element. It's concentrated. You have the neutrons and you have the protons, right? Those neutrons and protons are either a positive charge, proton, neutron, neutral state. Those make up the center mass of the electron. If they're going to create the mass, they also create the inertia of the atom, right? Because we know that inertia is related to mass. That means the greater that mass in the center, the more electrons are going to be circulating around it, right? Because it has a greater inertia, it's going to create a greater gravitational field. It's going to attract more electrons. We also have these quarks that are particles that make up the nucleons. We're not going to go that far in depth with physics, but just know they exist, right? We used to say that, electrons, neutrons, and protons were the smallest parts of an atom. We now know there are smaller parts of those that make up those neutrons and protons. Then we got our electrons that circulate the nucleus, and they provide the negative charge for the atom. So that eventually allows the atom to be neutrally charged, right? equal number of electrons to protons. Those electrons are organized in a shell. So the first shell has 2 electrons, the second has 8, third has 18, and it kind of progressively goes out there till we get out to the last one. Typically we talk about as the 7th shell, and that usually has 8 electrons out there. That means in order to have a stable element, it's always going to try to move towards filling out that outer valence of electrons. That's how we end up with those ionic bonds, which we'll talk about in anatomy. It's always trying to fill out those shells so those shells are stable. If you have a shell on the outside that maybe is supposed to have 8 electrons and it only has 6, the atom doesn't feel comfortable. So it's going to try to gravitate towards something where it can take and bond with 2 electrons to make that outer shell feel comfortable. It has to do with the gravitational inertial pull of that atom. So those diameters of those outer electron shells are determined by the amount of electrical charge in the nucleus. They gradually decrease from across the periodic table. This kind of shows what these atoms look like. Right? When we get down to potassium, potassium looks a lot larger than sodium, right? Na is sodium, potassium is K. Calcium slightly smaller than potassium, but slightly larger than sodium. This is why when you guys are going to talk about the sodium-potassium pumps in anatomy, you'll see how the body reacts to moving these specific elements across the membrane border to allow charges to propagate down the neutron, or down the nerve. Yeah, the neutron, the nerve. So as the nuclear charge increases, electrons are added to the outer orbit, the inner orbit shrinks. So as we add more valence electrons, the inner orbits shrink down. And you can almost think of that like the planets, right? If you look at the rotation of Mercury around the sun, it has a smaller orbit than we have. Because the closer you get, the less that orbit's going to be, right? So you have Mercury has a smaller orbit, you got the Venus. Venus has a little bit larger orbit, and you just kind of go out. And as you go out and you get out to, Neptune, it has a much larger orbit than the rest of the planets. That means it takes longer to have a year out there. Well, why is this important? Well, we're going to talk a lot about ions, right? Which we showed that chart before with positive and negative charges. All of those items are ions. They have a charge to them. Right? A positive ion has a deficiency of electrons, so it's missing outer valence electrons. A negative ion has an excess of electrons, right? This is just like you guys all heard about the 2 oxygen molecules walking across the campus, right? One of them says, hey, there's that hydrogen molecule that stole my electron. The other says, are you sure? The first oxygen molecule goes, yeah, I'm positive. No, that'll sink in a little bit. All right, Diana got a little bit of it. So as those electrons are given up or absorbed, the atom becomes an ion. That's different than isotopes, right? Isotopes are atoms of the same element with a different number of neutrons. So the electrons, the protons stay the same, but the nucleus itself is getting larger, right? So as that mass gets larger in the center, what's going to happen to the orbit of the electrons, do you think? I think Diana said something, but she's on mute. So
is it going to get smaller?
It's going to get smaller, right? Because those electrons are going to get sucked in a little bit, right? It also makes them a little bit easier sometimes to bond with other things. So if we have an iron isotope with 26 protons that has 30 neutrons, normally it'd be 26 and 26. In this case, it's got 30. So we often refer to it as iron 56. So we refer to it as the mass of the actual isotope, right? We may use isotopes in things like barium swallow tests. Has anyone ever seen somebody get a barium swallow test before or had it before?
No.
It's where you'll swallow barium, which has a slight radioactive charge to it. And they'll be able to X-ray so that as you swallow, they can see how your esophagus is contracting and expanding, pushing the food down to your stomach to see if there's a problem with your swallowing, right? Maybe somebody has had a stroke. Sometimes strokes can do weird things to the esophagus. Maybe the upper muscles of the esophagus aren't working, but the lower muscles are. So they may lead to patients choking because they get the food back there and they'll say, it doesn't feel like it's going down. And so they'll do a barium swallow test where that goes down, and they use a specific isotope of barium that is nuclear in nature, but not radioactive in nature. So the neutrons themselves help keep it from being radioactive, because obviously the last thing we really want to do is swallow something that's radioactive. That just sounds like a bad day.
So do those patients have to eat through a tube the rest of their life?
Maybe, it depends. What's going to happen is they're going to get that barium swallow test, and then they're going to see SLP, speech language pathology. And they're going to hopefully teach the patient how to re-strengthen that upper part of their esophagus. You know, if that's not possible and that top part kind of died off, then yeah, they may have to be tube fed or go to an all liquids diet, right? Which I don't think would be fun, because if you ever go to the hospital and you see somebody on all liquids diet, it's not a lot of fun. Right? Or the soft foods diet, which is basically like the consistency of baby food or Egyptian food, right? It's just mush. You know, I've had a patient that actually craved steak so much, he had his family make him a soft food steak. They mushed up the steak into basically goo. And I'm just like, that's not steak. That's, no, it's just not steak. Steak is steak, right? So yeah, I mean, it could be that. And it, you know, it depends on what part of the esophagus is paralyzed. You know, if it's further down, that could really cause problems, because as they swallow, that bolus will move down and then maybe get lodged. And sometimes that happens to you guys too. Did you ever do that where you take a big swallow of something and you get that really bad pain as it just kind of goes the whole way down? Because for whatever reason, your esophagus decided that day it's not going to work right. And then finally, like, you're just praying, like, okay, please get to my stomach, please get to my stomach. And then it finally hits your stomach and you're like, oh God, I'm never going to eat anything again. That happens even in normal people. Sometimes the esophagus just gets a little bit of dysphagia, right? Difficulty with swallowing, and it just acts up. Could be that, you know, the body's prompting oxygen over swallowing. It could just be your esophagus is being weird and spastic. But sometimes if you do have that, if you have that where that becomes paralyzed at the top, yeah, you're going to be on tube feed or a peg tube where they put the actual tube right into your stomach and they just feed you peritoneally, which is loads of fun as well. So we talk about compounds and mixtures, and you're going to see this lecture itself is about 5 chapters, because I combined the atomic nature of materials, solids, liquids, gases, and plasmas, because we don't need to know that much. We're not a full physics course. This is a get you to be a physical therapist physics course, or physical therapist assistant, not get you to be a nuclear physicist. It's not what I'm intending to do, you guys. So I hope you appreciate that. And you'll find really quick, if you look at the quizzes and my tests, if you look at the PowerPoints might guide you to what you need to study for the test and quizzes. I'm just saying. So, you know, do you have to read the book thoroughly? Absolutely, probably not. It's a good reference, but I use the book to make all of these slides, or most of them, because some of them I did add some PT elements to them. So compounds and mixtures, right? When atoms of different elements bond together, they make a compound, right? Salt is an excellent example of a compound. It's sodium and chlorine, right? What would happen if you would swallow a solid, just either solid sodium or solid chlorine? What could happen to you?
It would burn.
Yeah, you have problems, right? Sodium could cause an explosion, right? And chlorine is in bleach, right? The chlorine bleach is a form of chlorine. So either of those separately, literally, you could die from taking them. But when you combine them together, they make salt, and they're fairly safe, right? So that begs a question, because we talk about salts, but there's a lot of different salts out there, right? Because we have table salt, we have rock salt, we have pink Himalayan salt, which is nothing more than fancy colored salt, but that's beside the point. It's still sodium chloride. That doesn't change. It's just sourced by gurus on the side of Himalayan mountains, I'm pretty sure, or made in, you know, some factory somewhere. One of the two. I'm not sure which. But what makes salts differently? You know, what's the difference between a kosher salt and your traditional table salt? What changes that? What would make them different? Anyone have any ideas? Well, it could be the isotopic makeup, right? Maybe this form of salt, the sodium has an extra neutron, right? It could have more sodium, right? The sodium could be a stronger bond of sodium. Could also be that instead of sodium, you've got potassium, right? Potassium chloride is a salt. So there are different forms of salts. The typical salt we think of is NaCl or sodium chloride, mainly because that's what makes our food taste savory, right? That's why we add salt to stuff. It makes a savory taste to it, right? And we like savory. Our tongue likes savory tastes. Where I went to, I worked in Denmark and I lived in Denmark for a few years. They have a very specific candy that maybe if we ever get back to campus, I'll share some of them because it's one of my favorite candies to eat. They have what's called salt licorice, which is salt licorice. So it's black licorice, and on the outside, it's got a coating of salt. And it sounds weird, right? I had Jason's face initially too when I heard about that. Until you try them. Because the salt marries really well with kind of the acidic taste of the aniseed in the center and the sweetness. And you can eat, at least me, I can easily eat a full bag of them if I'm not careful. And then end up with mouth sores from the salt.
Those, like Mexican candies.
What'd you say?
Is it kind of similar to those like spicy with sweet Mexican?
Yeah, exactly. It's a spicy sweet type idea. This is more of a savory sweet type idea, right? So we add those, right? You can add like somebody was just talking to somebody the other day that was making jalapeno brownies. And I was really confused by that because I'm like, yeah, bold move. Exactly. I was really confused. They're like, no. You've got to understand that the spiciness marries with the chocolate so well. I saw it on Chopped or something like that. I'm like, nope. No, thank you. Chopped has a lot of stuff on it that I'm never going to see. But yeah, so we have salt, which is an idea of a compound, right? There's many compounds out there. And actually in the medical world, we have whole pharmacies that are designed to make compounds, right? Compound pharmacies. What makes a compound pharmacy? Maybe let's say you get a medicine. You're ordered to have penicillin. Why might you go to a compounding pharmacy for your penicillin versus just going and getting the pharmacy brand penicillin? Does anyone know what's the difference? The additives, right? When you mass market penicillin, you've got to add stuff in to make it preserved, right? But those preservatives sometimes react differently to people. Did you ever have a brand of like ibuprofen that just didn't sit well with you? Maybe you got, Walmart brand ibuprofen and it just didn't work as well as, Advil. What's the preservatives in it that kind of affect that, the stuff that holds it all together? In a compounding pharmacy, they can take some of those out and just make the medicine for what you need because they're making kind of a fresh version of your medicine. So they're a boutique pharmacy, but for some people, especially people with stomach issues, those compounding pharmacies can be really, really life-saving because they can mix in stuff that keeps you from getting sick from taking the medication. Maybe somebody that's got a cancer patient that every time they take their meds, they get nauseated. Well, they can compound in some anti-nausea meds. That way, when they take it, they're more likely to hold it down. And then we have the mixtures, right? The substance that doesn't chemically bond is a mixture. And when I think of a mixture, I think of what kids do all the time when they see the soda fountains at like Pizza Hut or down at your local AM/PM, right? It's where they go up with the soda cup and just start mixing in the sodas. None of that should ever be mixed together, but they make this makes a mixture, right? No one should ever mix Dr. Pepper with, Mountain Dew, but to kids, for whatever reason, that sounds like a good idea. A mixture of stuff that doesn't chemically bond, right? Some of the alcoholic drinks you can get down at, the local bars and stuff like that are mixtures less than compounds. And you can usually tell that when the alcohols don't mix well and you get that kind of effect where something's floating in it. Bailey's is an excellent example. If you mix Bailey's with a lot of other alcohol, you kind of get that what I call the floating brain effect, where it looks like something's curdled in your alcohol. But air is an excellent example of a mixture, right? Because there's so much around us in the air with just various gases, from our noble gases all the way up to our harmful gases like radon and carbon monoxide. So when we breathe in, I take a breath in to teach you guys. I'm not just taking in oxygen, right? I'm taking in carbon dioxide. I'm taking in nitrogen. I'm taking in radon. I'm taking in argon, right? All of that's being taken in. Well, how does my body know that it needs the oxygen? So it gets down to my lungs. What happens at the lung level that tells it, oh, okay, this is what I want. This is not what I want. What's your blood, right? Specifically, which blood cells?
Red.
The reds, yeah, right? The reds have that hematocrit and hemoglobin in them that helps suck that oxygen out of the air we're breathing in down at the little itsy bitsy alveoli in our lungs, right? You all seen pictures of the lungs that looks like a giant tree. And you get all the way out to those little tiny branches where those air bubbles are. It's really, really small capillaries or blood vessels around those little air bubbles. And when they get filled up with air, the blood that's around them is permeable. So it says, I want to suck up that oxygen and take it to the rest of the body. The downside is because we breathe in air that is an admixture, right? It's just a bunch of everything. Sometimes it gets really difficult for that blood to tell the difference between certain elements, right? Carbon monoxide is an excellent example of it. Carbon monoxide versus carbon dioxide. Carbon dioxide, 2 oxygens. Carbon monoxide, 1 oxygen. When you get down to those red blood cells, they have a hard time differentiating between oxygen, O2, and carbon monoxide because structurally they look a lot alike. That's why, if you're ever in a room that's heavy in carbon monoxide, you'll eventually pass out, right? It's not because of a lack of oxygen. What it is as you're taking that in, the body is flooding the rest of the body with carbon monoxide and slowly poisoning you. Right? That's why some homes usually have radon detectors and carbon monoxide detectors, specifically usually around the heaters, right? Especially if you're back east where I'm from, where we have oil heaters or natural gas heaters, because the byproduct of burning that is carbon monoxide. Where else do you encounter carbon monoxide?
Cars.
Cars, yeah, right? The cars release a lot of carbon monoxide. That's why you're told not to heat up your car with a closed garage, right? Not that we ever heat up cars here in Nevada. But if you're back from where I'm from, and the winters get to be minus 15 degrees, sometimes it's nice to go out and start your car and get it warmed up for you. So when you get in, it's got heat. Some of you are like, yeah, I do that in winter here. No, it's not ever that cold here. But if you run your car in your garage, all that carbon monoxide builds up in that garage, and you can actually kill yourself that way if you get in your car and don't realize the carbon monoxide's there. You need to have it venting out. If you've ever, I worked part-time at a repair shop once, and when they're working on cars and starting cars, the first thing they have to do before they start the car is run a little tube up to the back of the tailpipe so it vents all the gases outside of the building, because otherwise everyone in the building is going to get a little bit high and eventually get sick from that carbon monoxide. It's just because of that admixture. Now, let's say you're here in Nevada and you decide to go up to Denver, right? And you're going up there. I don't know why you're going up there. You're going up to visit family, but you're a runner. And all of a sudden you decide, I'm going to go out running in Denver. What happens?
Hard to breathe.
Yeah, it's hard to breathe, right? Well, why is that? Altitude, right? The higher we go up, the gravitational pull is a little bit less. So that means those oxygen molecules are farther apart. It means as you're breathing in the air, you're getting a lot of the larger molecules. So the nitrogens and stuff like that, not harmful to you. It's just harder to steal that oxygen and inflate your lungs and get them built up. Now, if you live there long enough, you acclimate, right? And sometimes if they come down to our level or come down to something like New Orleans where it's sea level, they'll often say it's really heavy for them to breathe because the air they're breathing is a little different than where they live. I went on one of those hikes down in Peru where they have Sherpas that help you carry all your gear. Why do you have to have a Sherpa to carry your gear when you're going down to places like that? Well, because you're going so high, our bodies are not made, what I was joking with one of them, they called us flatlanders, even though we're not really flatland here, right? We have mountains all around us. But they joke and say that we're flatlanders because we're so used to being closer to sea level that they're used to being up in the elevation. They can breathe really easily up there. And it carries oxygen. There's also medications that can help you with that as well, which they use in the military as well. But that admixture is why it happens, right? The air is not pure oxygen. So why do you think it is when you go into the hospital, one of the first things they usually do to you is throw a nasal cannula on you and pump oxygen into you? So they give you 2 liters of oxygen. Why do you think they try to give you supplemental oxygen, especially with COVID?
Because you're suffering from hypoxia.
Yeah, because a lot of our cases and a lot of our diseases, you end up with a hypoxic event. You're not getting as much oxygen absorbed. So how do you resolve that? Well, you flood the lungs with oxygen and you make it more prevalent so that the red blood cells say, oh, look, there it is. I need to take that, right? Patients that have COPD, another example of that, right? Once they have COPD, they're not able to get that air out of their lungs. So the air that sits in there is stagnant and mostly carbon dioxide. That's why they get hypoxic, is because there's not enough oxygen to absorb. So we got to teach them how to get that CO2 out. So molecules are 2 or more atoms bonded together, right? We have pneumonia, right? Pneumonia? No, ammonia. I always love that when patients tell me, that doc said I got ammonia. No, you don't have ammonia, right? We were talking a little bit, and we're talking about bones coming up here. I always tell the funny story I had was, it was back before the pandemic. It was about a year ago now. I went and saw a patient out in the patients say the darndest things. Went and saw a patient out in Pahrump who his wife's out in the kitchen, and I can hear her already laughing, and I don't know what she's laughing about. But he's like, yeah, the doctor said I tore my labia in my shoulder. And the wife is just dying of laughter out in the kitchen. And I'm like, the doctor told you tore what? Okay, some of you are getting it. It's like, yeah, my labia. And suddenly the wife's like, come here. So I get up and she goes, don't tell him it's a labrum. Keep him saying labia because it's hilarious. Labia is definitely not in the shoulder. For those of you that hopefully Dr. Johnson will teach you where that is. The labia is not in the shoulder. But the wife loved it. Patients say the darndest things. So it's very common when you have patients that's got pneumonia that'll say they have ammonia. Well, most of us have ammonia. It's in Windex, right? But this molecule is made up of 1 atom of nitrogen, 3 atoms of hydrogen, right? It's a really good cleaning solution because it lifts off grease off surfaces. I'm glad I made some of you laugh. That was the point of that story. So chemical reaction. That occurs when 2 atoms rearrange to form different molecules, right? Pulling apart molecules requires energy. Atoms don't like to separate. They like to attract to each other, right? But occasionally, during things like photosynthesis, the sun, as it gets absorbed by the chlorophyll of plants, breaks down carbon dioxide and releases a side effect of carbon, which builds up in the plant to provide its nutrients, right? And O2, which is what we breathe. Again, we talked about that briefly with energy, right? The more plants we have, the cleaner the air we breathe is, which is kind of some of the downside to living here in Vegas because there's just not a lot of plants around here, right? All the plants we have are transplants pretty much. Get it? Transplants. But there's not a lot of vegetation around here. That's why when we have conditions where we get like that smoggy effect from the wildfires and that, it kind of lingers in this area for a while. We don't have the plant material to kind of absorb it and break it down. And then as we combine atoms, right, it releases some of that energy. When oxygen combines with iron to form rust, there will be a byproduct of heat. If you're actually able to watch iron rust over time, and you were able to watch it on a thermal camera, you'll see that it slowly releases a small amount of heat as those atoms combine. So matter versus antimatter. Well, everything matters, right? But matter and antimatter are different sides of a coin, right? Atoms comprised of positive nucleons and negative electrons are matter. When we talk about antimatter, this is the opposite. Now the nucleus is negative and the electrons are positive or positrons. this is a real theoretical part of science here, right? But we know, and we know from looking at the CERN collider and stuff like that, that both matter and antimatter can't exist in the environment at the same space and same time, right? We think that's how black holes are formed, right? We think that what that is a combination of matter and antimatter forming a black hole. Well, why do we think that? Well, because we still don't know what a black hole is, right? Does anyone know what happens if we send something through a black hole? Nobody knows, right? We don't know what happens to that object. So that's where we talk about the difference. So true matter is what we deal with on a daily basis. Positive nucleus, negative electrons. Antimatter is the opposite. Negative nucleus, positive electrons or positrons, right? So when we talk about positrons, they're the same mass as an electron, but they're reverse charged. And then the antiprotons are the same mass as a proton, but negatively charged. The main theory here is if you combine those two, the nucleuses will collide and cause an exothermic reaction, which will cause massive explosion, right? Which we wouldn't want. And still, we're still trying to do that in CERN collider. And I sometimes question if that's the best idea. Right? We're trying to see what happens. We're going to keep it in a controlled environment. We're going to put it in the collider where it's protected by titanium tunnels. But really, I'm not so sure it's a great idea to start doing this. We could cause some problems eventually. It's science. Yeah, it could also blow up the Earth. Dark matter, right? Dark matter is unseen unidentified matter from elements that comprise about 23% of the universe. So we know that dark matter exists. We also know that dark energy exists, which is anti-gravity effect of dark matter. So if gravity attracts, what is dark energy going to do?
Repel.
Repel, right? So some of the theory in that is that, well, maybe dark energy itself is nothing more than a lot of antimatter gathered together. And that would make sense if the matter and antimatter would repel each other. Finding the nature of this dark matter is really kind of a high priority right now because we want to know where we can go in space, right? Because eventually, sad to say, we're eventually going to need a new planet to habitate because we're really good at destroying planets, right? Eventually, this planet won't be able to sustain life. So the problem we look at is, well, what happens when we send a group of people off into space and they encounter some of this dark matter or dark energy? What does that do to our living being? And we don't really know that yet, right? That's why they're researching a lot of this. The other thing is, if we can figure this stuff out, it may lead to stuff like quasi-dimensional spaces and all kinds of cool science like that goes along with string theory. So a lot of what we've learned in 2050 will likely dwarf what we know now. And that's kind of the nature of science. As we progress, we take these leaps and things change. You know, I'm not saying in 2050, we're going to be Starfleet in Star Trek, right? Where, you know, money is not important anymore. We're researching space, we're encountering alien beings. But what we know then will likely change the way we are now. Hopefully we've learned by 2050. Hopefully we're not still doing the stupid stuff we do now. So let's talk about the actual structure of matter when we talk about stuff like solids, liquids, and gases. So when we talk about solids are atoms that end up arranged in a regular array, right? Those regular array typically form crystals, right? If you look at salt under a microscope, has anyone ever done that back in elementary school? It looks very crystalline. It almost looks diamond-like. That's the normal arrangement of matter. Sometimes atoms don't arrange in that matter and they become amorphous solids, right? That's what we talk about, that kind of gooey gunk, right? When you think of amorphous solids, I always think of Slimer from Ghostbusters. He's an excellent example of an amorphous solid, obviously solid, but he's also a goo. One of the main properties of solids is density, right? And this isn't how smart or dumb you are. That's a different type of density. This is the actual effect of how compact items are. When we think of in the physical therapy world, we often think about the difference between density and porosity, right? Dense is where everything's kind of compact and pushed together, right? As this little brain thing here is, it's less dense here than it is when I squish it all together, right? It's more porous when it's outside. There's space between the molecules. So fats, for example, are solid at room temperature, right? And cannot form and become liquid, or can become fully solid the colder we make it, right? We have olive oil, less dense than butter, which is why a lot of times we talk about olive oil for cooking is better than butter, because butter has a little bit higher cholesterol. That's why it's a little denser, right? And also tends to stick in our blood vessels a lot more. Iron is denser than wood. That makes sense. And you can kind of see that, right? We still build structures out of wood, right? But you don't see any sky-high skyscrapers built out of solid wood. That would kind of be like the Three Little Pigs, wouldn't it? Building a skyscraper out of wood, eventually the wind's going to come along and knock it over. So we build a lot of our structures out of iron and iron, substitutes. So in the human body, overall, our density changes because we're cellularly dynamic beings. That literally means we change over time. So when we're young, bones are less dense. That allows us to grow. As we get older, our bones start becoming more and more dense. And then eventually what happens to those bones again? They become less dense, right? They become osteoporotic, porous. So the bone is a great example of density. The denser your bone, oftentimes the heavier you are as well, right? But also the more solid you are, right? That you're able to bear weight a little bit better, sometimes have less pain, all that. So as we talk about adults, as we age, once you hit kind of that 30s, your bone structure starts going downhill, right? Until you hit your 60s, you're starting to really become osteoporotic. And as you get older, you become more osteoporotic. That's why when you fall in your 60s, it's a lot bigger problem than if you fall now. And that goes along the idea of fractures. As we are now, and I'm not saying I'm as young as you guys, but I'm still young compared to 60s. If we fall right now, the most commonly fractured bone we're going to fracture is in our hands, because we're going to probably fall with our arms out like this. That's the fallen outstretched hands. But as we get older, believe it or not, the more common bones that we fracture are our hips. And that's because they become less dense. Our bones themselves become more porous. As they become more porous, it's more likely to fracture. In order for density to increase, we have to provide a stimulus for it. So what do we do that stimulates our bones to get thicker? What can we do?
Exercise.
Exercise is a great example, right? Something as simple as walking. Or even if a patient can't walk, standing, right? It's amazing what just getting a patient standing can do to the density of their bones. The more we spend bedridden, our bones start becoming softer, more likely to fracture, right? The units of densities are typically kilograms per meter cubed or grams per centimeters cubed. You don't have to specifically know that. But when we're talking about density, we're talking about the mass of an object versus the space that it occupies, right? So if I say which is heavier, a pound of fat or a pound of bone, which is heavier?
A pound of bone.
They're the same.
They're the same. They're both a pound. The mass is the same, right? But if we talk about the density, how much the stuff is packed in, which is denser, fat or bone? Bone's going to be a little bit more dense, typically, unless you have really porotic bones. But it's going to be more dense because the molecules are closer together, right? That's why we tend to gain fat, but we don't gain bone, right? Bone is what it is. But we can put on a weight and gain fat pretty easily by just overeating or not exercising. I'm starting to feel self-conscious here thinking about it. So here we're looking at some bones, right? And as we look at the first example of a bone up here, right? That bone looks nice and cortical and packed in. Then we get down here and we've got the bone starting to break down. The bone is actually starting to be reabsorbed by the body, and you're starting to become more porous. There's more space in that bone. If it becomes like this, would it make sense that it would be easier to fracture right through that if it's not solid? Right?
Yes.
Think about it. If I give you a 3-foot rod of steel and a 3-foot piece of wood, and you bend them both, which is going to be easier to bend? The wood. The wood's eventually going to snap too, right? Because it's porous. It has a little bit more space between the molecules, unless I give you something like ironwood or something like that. So the more that we can get those bones to absorb and keep everything in them, keep that calcium, keep the vitamin D in there, and keep those bones solid, the easier it is to prevent us from getting fractures, right? That's why when you get older, a lot of times the doctor's going to prescribe for you to take supplemental calcium and vitamin D, which they usually take Oscal D, which is one of the common over-the-counter medications for that, right? And the idea is hopefully we can get our bones to be a little bit more compact and protect us from fractures. Who is more likely to get a fracture over 65, a man or a woman?
Man.
Okay, so I got one vote for a man. Do I have any vote for women?
Woman. Woman.
Okay, so I got a woman. Okay, so we got
Women.
both. All right.
Woman.
So a man is more likely to still fracture bones from being stupid. That's typically the way, honestly, that's a lot of the way men end up with they're cleaning their roofs, right? Or they're cleaning their gutters and up on the side of the building. Women are more likely to get fractures because their bones are more porotic, right? Because unfortunately, ladies, your hormones, as you get older, affect the porosity of your bones. And your bones overall become weaker. And that's just a side effect of estrogen and all those fun chemicals that make you female, right? But the docs can supplement that. There are all kinds of medications now they can give you that actually help keep you a little bit more solid as you get older. But I always joke that men tend to have more stupid fractures. Women have more, I sat down and I don't know how it happened fractures, especially over 65. I had a lady once that literally had 4 sections of her vertebrae fractured, and the only thing she did was sat down in her chair. It's like, I don't know how it happened. I sat down. I'm like, did you like jump off a 3rd-story building into your chair? I don't, and her bones were just that porous. And if you look over here at that second example I have here, look at how holy, right? These vertebrae are getting ready for Catholic Mass because they're holy. There's all kinds, okay, I made somebody laugh. Have they made any medications to help us out with stupid fractures? I know that we have some that if we don't take them can help us prevent stupid fractures. You know, ethyl alcohol helps us avoid stupid fractures. I'm just saying. They haven't gone about anything to make us smarter. I mean, contrary to what Prevagen and all those medications say. But you can look at what the porosity of that bone has done to the top of that vertebral body. It's collapsed it. Right? So that means every time this person's sitting down, those bones are unevenly wearing, and they're eventually going to lead to a fracture of the spine. And you can even see when we come down here, it's starting to happen in some of the other vertebrae, right? That's literally going to lead to spinal fractures from patients doing something as simple as sitting down. So properties of solids, right? They form bonds. And in anatomy, you probably, I don't know if you have yet, but you will talk about ionic covalent bonds, right? There are also metallic bonds, obviously, that form in metals. And then there's the van der Waals. They're there, just know they exist. We're not going into that part of physics. Just don't worry about it, but they exist. The main things when we talk about in anatomy, physiology is the ionic and the covalent bonds, the way things shape together. The properties of a solid are dependent upon the bonds that exist, right? We get down to those van der Waal bonds, they're really easy to break. As those bonds get firmer and firmer in the covalent or the ionic formation, they get harder and harder to break, and that allows things to be a little bit more solid. So moving from that property of density in solids into elasticity of solids, right? Elasticity we often think of as the ability to stretch, right? I don't have a rubber band here, do I? No, I don't. The ability for something to pull apart, right? Really, elasticity is the meaning that if we pull it apart, that it returns to its original shape. So it's the ability to return to its resting size is elasticity, right? A spring can be compressed or stretched, right? But cookie dough, if we compress it, we squeeze it together in a ball, it doesn't immediately return back to its shape. That's not the way cookie dough works, right? For those of you that know, that's the stuff that you're supposed to eat raw, right? So cookie dough itself is inelastic. This object here that I have, this stress tool, is very elastic because I can squeeze it down and it pops back out into original shape. Eventually, if I squeeze this enough, what's going to eventually happen to those bonds in it? Well, they're going to break down and this won't return to its original shape and it'll become useless to me. That's why I have about 50 of these, because I do go through these just from stress. In human bodies, some tissues are more elastic than others. So which do you think would be more elastic, a bone or a ligament? Which is going to return to its original shape best?
Ligament.
Ligament, right? And we have kind of a hierarchical structure of how things go elasticity-wise, right? Muscles are very elastic. Ligaments are very elastic. Tendons are very elastic. Bones, not so much. If I take a bone and start bending it in half, if I let it go, there may still be a slight curve to it, right? Or worse, if I bend it hard enough, it'll snap. So materials that aren't able to return to its original shape are considered inelastic, right? So here we have kind of the breakdown as we're looking down through. So bone is our most inelastic. It does handle some tension. And when we are a kid, it's the most elastic, right? How many of you have seen a kid that have like fallen down a flight of stairs, hits the ground, bounces right up and goes off running? Like nothing ever happened. We do that, we're going to the hospital for a couple weeks, right? Because our bones have become more inelastic. Kids' bones are, we like to use the term softer. Softer is not really a good term. I like to think of them as greener, meaning that they're less likely to fracture under this stuff. Can kids' bones still break? Absolutely, right? And there, we see that unfortunately a lot in dealing with child abuse cases, right? Kids' bones still break. I guarantee if a kid comes in with a fractured forearm, the first thing we're not thinking is, oh, that kid fell and broke his forearm, because usually if you fall, their bones are elastic enough, it's going to absorb that fall. If you've got a fractured forearm, it's usually a case of child abuse, usually. Skin. Skin is somewhat elastic, right? Because as I'm moving around here, my skin is changing shape. But if you stretch it past its long-term stretch, it won't return to its original shape. Have any of you ever seen somebody that lost a significant amount of weight, like 200 to 300 pounds? Does that skin suck right back up in and becomes nice and firm? Right? They usually have to have surgery to remove those excess folds of skin, especially if they've lost a lot of weight. Just because the skin has been stretched to that point, it can no longer actually return to its original shape, right? If you take a rubber band, actually, I do have a rubber band here. I have a hair tie. I don't know why I have a hair tie. I don't have any hair, but I have one, right? I can keep stretching this, and this is returning to its original shape. If I keep doing this for a long period of time, this is eventually going to wear out. And then as I stretch it out, it'll stay in its elongated form. That's kind of like skin. If I take something like a pair of scissors here, and I'm not actually going to cut myself, don't worry, but I open the blade up and I push it into my skin, will I immediately cut myself? Not immediately, right? If my skin is healthy, it'll deform first until I reach that point where that skin can no longer be deformed, and then it'll cut. Paper cuts, great example of this, right? Anyone ever grab some paper and get that nice, just slice right through your finger? Like, how did that happen? Well, it was just quick enough and sharp enough that it cut through your elastic barrier of your skin. And then you find an orange and it really hurts. An orange, you're glad you found it. Tendons, somewhat elastic, right? But we have sensors in tendons that detect when the stretch is too high in order to protect them, right? Also, if you have too much of a pull on that tendon, it can actually pull off the bone. And it will call what's called an avulsion tear. And usually takes a little part of the bone with it, right? You'll see this occasionally in the Achilles tendon, especially in athletes, where maybe an athlete jumped up to do a jump shot in basketball and they were trying to clear somebody else. So they put some extra oomph behind their jump, and that Achilles tendon will literally rip off the calcaneus, right? And it kind of rolls up. They're going to have surgery to repair that. The biceps, I've seen that in the gym with a lot of stupid people lifting. When they're doing lifts and they lift too much, and they're not listening to that bicep telling them that's too much weight, and they get what's called a Popeye tear, where the bicep rips off the distal arm and it rolls up and they get a big muscle up here, right? But that's not actually muscle. That's now all of that bicep rolled up into a chunk. And well, they're not going to be lifting for a while because they're going to need surgery. Right? Ligaments. So remember, tendons are muscle to bone. Ligament is what?
Bone to bone.
Bone to bone, right? When we talk about something like the ACL, the anterior cruciate ligament, it's attaching the tibia to the femur. So you've got two bone-to-bone connections. The ligaments are somewhat inelastic. They're less elastic than a tendon, right? They have a small degree of stretch, but their main purpose is an anchor. It protects those bone surfaces. So there's not a lot of shearing going on in the bone. If you give too much force, it will tear, right? And funny thing is, if you look at most of your joints, so if you look at the shoulder compares really great to the hip as far as the tendons and ligaments. If you look at the elbow, it compares to the knee, right? The knee has an anterior cruciate ligament. The elbow has a cruciate ligament, right? The knee has an ACL and an MCL. The elbow has an ACL and MCL. Those are designed so they function structurally the same. The only difference is our elbows go like this versus our knees go backwards, right? It'd be really weird if our knees went the other way. We look like chickens, I guess, or something. No, chickens even have that. What would look like that? I don't know. Anyway, thoughts for another day. And then muscle, right? Muscles are kind of our most highly elastic tissue we have because they also have to contract, right? They can only lengthen, but they return to its original shape pretty easy. They can also become smaller and they can also become larger, right? They can get hypertrophy, right? Shrinking, or hypertrophy, where they grow, right? You go to the gym and you get swole, you're actually increasing the size of those muscles. Does that mean, like, say you go to the gym and you go and you start lifting and you're starting to get those biceps coming out and the shoulders popping out? Does that mean that there's more muscle there? Does that mean you have more sarcomeres, more actin, more myosin? An emu, thank you, Sydney. That's what it was. I couldn't even think of it. Should have thought of lemur, the emu. Right, so say I go and I work out my delts and now my delts are popping off my shoulder. Doesn't mean there's actually physically more muscle there. What it means is you've caused the tissue that's there to grow. Now there is some growth there, but scientists argue about how much, right? So that literally means, does that mean that some people would have a body composition that would lean them more to becoming bodybuilders versus somebody that doesn't? Is there some science to that? What do you think?
Yes.
Yeah, there is. There's some science that doesn't mean that you can't get built, right? And it even comes down to genetics. When you look at certain genotypes and you're also talking about certain ethnicities, right? Based upon the different composition of the fat in the body, where there's brown fat or more white fat dependent, you can make those muscles pop a little bit more just based upon that alone. Right? That doesn't mean that if you're like, I'm never gonna get swole, so I'm never going to the gym. Oh no, you can still build up your muscles, right? Even if you have a nice protective layer of warmth over your muscles can still be strong. So just think of it that way, right? Just because I've got this nice protective layer over my belly doesn't mean I still don't do 500 sit-ups a day. I do. It's just that I've got a little bit more protection there from everyone else. Right? The muscles are there, they're just hiding. That's what I always tell everyone. Muscles are there, they're just hiding. I'm trying to stay warm, so that's what I need. So we'll talk about the concept of application of elasticity, right? Humans have muscular tissue that's elastic and contractile, right? each joint's acted upon by numerous muscles. When you think of the shoulder, you guys did you start to look at your list of muscles yet? Anyone freaking out yet about that? Yeah, right? When you just look at the shoulder, think about this for a second, right? So we look at the shoulder joint itself, right? We have our anterior, middle, posterior deltoid, supraspinatus, coracobrachialis, biceps, triceps, supraspinatus, infraspinatus, teres minor, and subscapularis, right? You have teres major, you have the latissimus dorsi. Just in that joint, you have all of those muscles, and not talking even about the scapular muscles that work with it, in that one joint, right? That work together to move that joint. It's, to me, the way the human body's put together is just an amazing machine. So when a muscle contracts, right? And this is to get you guys prepared for kinesiology and for anatomy. When a muscle contracts or moves something, that is called an agonist muscle. So in the muscle, like if I'm doing a curl, what muscle is moving my arm?
Biceps.
The biceps, primarily, right? Brachialis and brachioradialis as well, but primarily our biceps. That means our biceps would be the agonist there. It is the moving muscle. Every muscle that is a mover also has an antagonist, a muscle that restricts that motion. So the arm's an easy one, right? The biceps are maybe our agonist. What's our antagonist?
Your triceps.
Triceps, right? So as the biceps contracts, the triceps stretches, right? That's where we get this idea of active versus passive insufficiency. In active insufficiency, right? If the muscle cannot contract, cannot get any shorter, it is actively contracting, therefore it is actively insufficient. If a muscle cannot lengthen anymore, it can't get stretched any further, that is passive insufficiency. That goes along with this agonist and antagonist thought. So when you're thinking about this idea of active versus passive insufficiency, the agonist typically is going to become actively insufficient. The antagonist typically is going to become passively insufficient. So when we curl up like this, there are two things that can stop me here. Well, a couple of things, but my biceps that can't contract anymore, and it can't right now because I've got tissues going against it, right? If I could get rid of all the meat of my forearm here, I could actually get this to contract more. That means the biceps right now is actively insufficient. The other thing that could happen is, what if my triceps are tight? I may only get to here. My biceps still have room to contract, but the problem is my triceps are so tight, I can't curl anymore, right? That would mean that the triceps at that point is passively insufficient. It won't stretch anymore. There are positions we can put every muscle in to make it actively or passively insufficient, right? When we're actively working muscles, we're going to try to make them active insufficient. We're trying to stretch them. We're going to try to make them passively insufficient. Does that make sense, those two terms? Are we okay on those? I know it's going to have to be reviewed again. We're going to hit this. I hit this in physics. You're going to hit this in anatomy. You're going to hit this in kinesiology. So this is a kind of a thing that's going to keep coming back at you. Just saying. So when we talk about stuff pulling on solids, we talk about tension forces. When we talk about stuff pushing on solids, we talk about compressive forces. When we talk about that in the physical therapy world, when things are being pulled apart, we call that traction. When things are being pushed together, we call that approximation, right? There is another force called shear force, and shear force is when compression forces are parallel to each other and they rub, right? Going in opposite directions. That's the shear force. So when we look at these bones here, these bones being pulled apart are traction. When do we hear about traction a lot in physical therapy? Does anyone know?
Spinal decompression.
Yeah, spinal decompression, right? Yeah, when we're trying to separate those vertebrae a little bit to let them breathe a little, give those nerves a little room. Here, when they're coming together, right, we have compression. Right? And when we think of compression, we think of areas that provide the most amount of surface contact. Usually that's a protective phase, right? If I put a neck brace on a patient, I'm going to try to collapse their spine a little bit so that everything's more solid. They're going to compress a little bit. When we have shear, it's kind of like this picture down here with the knee, right? There's your problem right there. I'm just saying, that's not the way the knee is supposed to look. What happened at that point is those ligaments that were supposed to hold that femur in place have sheared off because of the force of that pull. Well, let's say we have this joint here, right? This could be the olecranon, right? And say we have that olecranon locked into elbow extension. If suddenly I was to apply a force upward and downward on the radius and the humerus, opposite, I would be providing a shearing force because it is compressed. That olecranon is going to snap right off, right? Because it's in that fossa, and you're going to end up with a compression fracture. You can get compression fractures of the spine just by, like I talked about before, sitting down like this, right? Where that spine just collapses. And as we get older, unfortunately, that's a real possibility. The last thing we'll talk about, and then I'll let you get your break, is arches, right? Arches are a design of solids to provide support. In the human body, we have one of the most famous arches, which is the foot, right? The foot is technically classified as a windlass system. You don't have to specifically know that. It's just a cool scientific fact about it. As the toes extend, the tissue in the bottom of the foot puts tension, the arch picks up, right? Sometimes people have high arches. Sometimes people have no arches. Ideally, we want a little bit of an arch. What's the point of the arch in the foot? Does anyone know?
Isn't it like an arch is the strongest shape, so it's the best way to support all the weight that's on top of it?
Exactly, right? It's pressure relief. It provides that compression support. So when we're walking, right, it helps distribute all that weight that we're pushing up through the leg evenly. That's why if somebody like me, who has a very, very flat foot, runs, I tend to get a lot of knee pain. But you can also have the opposite. If you have too high of an arch, you can also end up with some knee pain because the foot's not made to walk like that, right? Ladies, sometimes on Fridays and Saturday nights, if you're going around town, you might do something really mean to your foot to increase the size of your arch that causes you pain in the legs. You might wear heels, right? And if you ever question who designed heels, I'm pretty confident that was a guy that designed them because I don't think any lady would design that sort of torture on themselves, right? And if we have a problem with our arch in a foot, we can actually add support to it, right? We can put in inserts. And if we put in inserts, a lot of times we can relieve a lot of pressure throughout the rest of the leg. That arch is there to provide stability of the foot. It also redistributes force during walking. All right, so we're at 16 after. Let's pause here and we'll finish up on this next class. So stop share.